All right, now that we have reviewed our 5 general reaction types, we're going to get into stoichiometry and how we can make predictions based off of our calculations that we'll be making in this section here. So some assumptions that you should know that we'll be making before we get into our calculations here is that we will be assuming that reactions are spontaneous. So let's make sure we highlight this, that reactions are fast, they go to completion. So essentially what that means is they are going to, or your reactants are going to react completely and produce 100% products, okay? We're also going to assume that our reactions are stoichiometric, which means that we can use our mole ratio to calculate what the question's asking for. Okay. So what stoichiometry is that it's a branch of chemistry that deals with the relative quantities of reactants and products in chemical reactions. In a balanced chemical reaction, the relations amongst quantities of reactants and products typically form a ratio of whole numbers. Stoichiometry is founded on the law of conservation of mass, which just means that the mass of reactants is going to be equal to the mass of the products. So because we assume that we have a closed system, mass must be conserved. So in other words, what goes in must come out, or the total atoms of reactant is going to equal your total atoms of products. Now, when solving stoichiometry questions, we're going to be using 4 basic steps to handle all questions, okay? And the extent to which we use these 4 steps depends on the types of stoichiometry question that we're going to be given, okay? So step number 1 is always make sure you have a balanced chemical equation for your given reaction, okay? Step number 2 is you're going to need to calculate the moles of your given substance. So what your given substance is the substance that you are given the most information for. In step number 3, we're going to have to make some adjustments here. We're going to be using a mole ratio to convert moles of the known substance. So let's cross this out. To the moles of the unknown substance. Okay. And then step number 4 is just answer the question. So the reason why this step is left to be fairly vague is it just depends on what your question's asking for. If your question asks for the mass of your unknown substance, then you're going to convert moles into mass. If the question asks for a volume, then you need to convert from moles to volume. Okay, so let's write a summary of those 4 steps, because those 4 steps are pretty important. Okay, so step 1, you absolutely need to write a balanced chemical equation. Step number 2, find your moles of your known or your given substance. Step 3, use your mole ratio to convert moles of known to moles of unknown. So as a reminder here, your mole ratio is going to be using the coefficients from your balanced chemical equation that you would have created in step 1. So that's why it's incredibly important to start off these or solving these questions with a balanced chemical equation. But for the molar ratio, it's the coefficient of what you want. And maybe I should write coefficient here. So coefficient, which I'm going to have to abbreviate just to COEFF. So coefficient of what you want divided by the coefficient of what you are given. Okay. And then step number 4 is just convert moles to the units that the question's asking for. All right, so let's make sure to highlight this box because these 4 steps are really important. So we're going to start off with a mole-to-mole stoichiometry question. So in this first example, we have lithium metal reacts with nitrogen gas in the air to produce a black solid. How many moles of product is produced if 1.80 moles of lithium reacts? Okay, so from this example, you can see that the whole point of stoichiometry is to essentially help you be able to predict how much of one substance you should be able to get out of a reaction. Okay, that's the whole idea behind stoichiometry. So with this first sentence here, it gives us an idea for how to start our balanced chemical equation. So first we're starting off with lithium metal. So lithium, the symbol for it is Li. Since it's metal, it's a solid, and it reacts with. So we're going to translate that into a plus sign, nitrogen gas. So nitrogen, that's part of Hofbrinkel. So nitrogen, whenever it's by itself, there's always 2 of them, and since it says it's a gas, we're going to put it as a gas state. Okay. So the question doesn't tell us what our product is. We need to predict what the product is. Okay. So based off of our 5 general reaction types, if we look at our reactants given, we have an element reacting with an element. Okay, so this is going to be a formation reaction. So element reacts with an element to create some compound. Okay, so since we have a metal with a non-metal, we're going to want to pay attention to charges in order to balance them. So for lithium here, that's going to be one of our group 1 elements. So we can find lithium right here. And lithium likes to have a charge of +1. For nitrogen, if we look here, nitrogen is part of group 15. You can find it right here. So group 15 ions like to have a -3 charge. So I'm going to write this above. So +1, -3. We know that that doesn't equal 0, so we got to do crisscross applesauce. So I'm going to write the 3 behind lithium here. Okay. I'm not going to write a 1 behind nitrogen because it's assumed if you're writing the symbol for an element, there's at least 1 of them there. Okay. If there's more than 1, then you got to write a subscript behind it. All right. Now, it does tell us that the product is a black solid, so I'm going to write that this is a solid. Okay. So we don't need this right here above the lithium nitride, that was just to show you how I'm balancing the compound. So that's why I'm erasing that. But what we need to do right now is we have a skeleton equation. Now we need to make sure it's balanced. Okay, and we're going to balance this skeleton equation using coefficients, which are the big numbers that come out in front of chemical species in your chemical reaction. Okay, so sometimes what I like to do is put little spaces here just as placeholders for where the coefficients should be going. Okay, so I am going to arbitrarily start with nitrogen here, just because that seems like that might be a more trickier one to balance. Okay, just because it's got the 2 for the subscript there. Okay, so I have 2 nitrogens going in and only 1 coming out. So what that means is I'm going to have to put a 2 coefficient here to make sure I have 2 nitrogens going in and 2 nitrogens coming out. However, that 2 didn't just affect the nitrogen, it also affected the lithium. So now for the product side, we have a total of 6 lithium atoms coming out. So we're going to need 6 lithium atoms going in. Okay, and at this point we have the same amounts of each element going into the equation as reactants as are coming out as products. So this is completely balanced. Now sometimes what I like to do is I like to arrange the information that's given to me in the question underneath the chemical species it applies to in the reaction equation. Okay, so what I mean by that is looking at this last sentence here, it asks us how many moles of product, so moles, the symbol for our variable for moles is N, is equal to question mark, is produced if 1.80 moles of lithium reacts. So let's put moles is equal to 1.80 underneath lithium. Okay? So that's what I like to do just to organize my information. Okay, now let's get to solving this. So first, start out with your given number here. Okay, and just to go back to our steps, we have completed writing a balanced chemical equation. Now for step 2, it says find moles of your given substance. Well, they already gave us that number. Okay, so step 2, it's already been completed because the question gave us that number. So right now we're on step 3. We're going to use the mole ratio to convert moles of our known substance, which is lithium here, to the moles of our unknown substance, which is lithium nitride. So how I'm starting that off is I'm writing my given number, and I'm writing moles, and I'm going to write the substance. The reason why I like writing the substance is because what I find happens to students is they get so used to number crunching that they end up forgetting what substance their number belongs to, which can create some problems for calculations here. So that's why I like writing out the identity of the substance that the number belongs to. Okay. Now for our mole ratio, which is right here, we're using our coefficients from our balanced chemical equation. So remember, our molar ratio is coefficient of what we want divided by coefficient of what we're given. Okay, and since we organized our information underneath our balanced chemical equation, it makes it super easy to see what we want and what we are given. Okay, so we want lithium nitride, and the coefficient for that is 2. We're given lithium, and the coefficient for that is 6. So what I'm doing here is I'm taking 1.80 moles, timesing it by 2, and then dividing by 6. So if I showed you what that looked like in my calculator, what that would look like is 1.80 times by 2 divided by 6, and we get 0.6. So I'm going to write 0.6. Now, remember that anytime you do a calculation, you need to write your final answer in the correct amount of significant digits. Okay, so let's look at the question. And the only number they gave us was this. Okay, this number has 3 significant digits because 1 counts as a significant digit, 8 counts as a significant digit, and this 0, since it is a trailing 0, does count as a significant digit. So as a reminder here with the special case of zeros, trailing zeros that come after some digit that isn't 0, those count as sigdigs. What I call sandwich zeros, so they are in between 2 non-zero digits, those count as sigdigs. The only ones that don't count are leading zeros, so zeros that come before non-zero digits. So we want our answer in 3 sigdigs, but we want to keep the same value. So knowing that trailing zeros do add to the amount of sigdigs, I'm going to add 2 zeros, so our sigdigs are going to be the 6 and these 2 zeros. Okay, and whatever you do, do not forget about units. Our units are moles. Okay, and if we look back at our molar ratio and sort of use the substances kind of like units to show how they cancel out. So lithium is on the top and I see lithium on the bottom. So if I have the exact same thing in the numerator and denominator, those cancel out. Okay. And what we are left with is lithium nitride. So we have 0.600 moles of lithium nitride. And that's our final answer. Moving on to the next example here, we have how many moles of oxygen are required in the burning of butane if 2.50 moles of water vapor are produced. All right, so first step, let's create a balanced chemical equation. Now, we need to figure out, okay, what type of reaction is happening here. Now, the key word here is burning. That tells you that this is a combustion reaction. Now, for butane, how we're going to figure out what the chemical formula for that is we're going to go to our data booklet and go to our list of chemicals that are on page 4 and 5 of your data booklet, and we're going to go in and find butane. Now, these are arranged alphabetically, so butane is near the top, and it's on this line. So butane is C4H10. Okay. So butane, that's going to be our fuel that's burning. Now remember, for combustion reactions, you have your fuel reacting with oxygen, and for a hydrocarbon combustion reaction, you are always going to get carbon dioxide and water vapor. So with butane here, in the question it doesn't tell us what the state of butane is, but if you look at your Chem 30 data booklet, it does say that it is a gas, so that's what I'm going to use. Okay, so they react to produce carbon dioxide, which is a gas, and water vapor. Alrighty, so I think I'm gonna scooch this up a little bit. Okay, and now that we have our skeleton equation, we need to make sure that it's balanced. So for combustion reactions, you always start off with carbon first, then balance the hydrogens, then the oxygens. Okay, so we got 4 carbons coming in, we need 4 carbons coming out. For hydrogen, we have 10 coming in, we need 10 coming out, so 5 times 2, that's going to be 10. All right, now for oxygen, I'm going to start with the oxygens on the product side first. So remember, we have 4 times 2, so 8 oxygens coming from the 4 molecules of carbon dioxide, and we have 5 times 1 oxygen, so 8 plus 5 oxygens. Okay, so that is going to give us 13. Alrighty, so you may be seeing a problem here where we have 13 atoms of oxygen on our product side, but on our reactant side, we're only ever going to get an even number because of that subscript 2 on oxygen. Okay, now we can't change the subscript, but what we can do is we can take the number of oxygen that we got on our product side, we can go 13, and then divide it by 2. Okay, the reason why we're dividing it by 2 is because of the subscript right here. Remember that combustion reactions are the only type of reaction in which you are allowed to write a fraction. Okay. However, the next problem here is that back in our notes, we said that we're only going to have whole number ratios of reactants and products. Okay. Now, there's a problem here because we have a fraction. We don't have a whole number here. Okay, so how are we going to fix that? We're going to fix that by multiplying every chemical substance in this reaction by 2. And the reason why we're multiplying it by 2 is to get rid of this denominator. Okay, so if we multiply everything by 2, we're going to get 2 molecules of butane. We're going to get 13 molecules of oxygen. So how that's working out is 13 over 2 times by 2. Well, you could go 2 times 13. That's going to be equal to 26. Right? So with multiplying fractions, you multiply numerator with numerator, denominator with denominator. Okay, so that's why I'm getting 26 in the numerator, and then 1 times 2 for the denominator is just 2. Okay, 26 divided by 2, that's 13. All right. Now, the key here that people often forget is they forget to keep on multiplying the products by 2 for this trick. So 2 times 4, that's going to give us 8. 5 times 2, that's going to give us 10. Okay. So for questions where it involves a stoichiometric calculation, you are going to want to make sure that your coefficients are whole numbers. Okay, but if you are just balancing a chemical reaction and you don't need to do a stoichiometric calculation, for combustion reactions only, you are allowed to write a fraction for your coefficient, and it's only ever going to be on oxygen. All right. So, step 1, write a balanced chemical equation. That is done. Step number 2, find your moles of your given. Well, moles of given were given in the question. So, I'm just going to write that underneath. So, we have 2.50 moles of water vapor. Okay? Now, what are we looking for? We're looking for how many moles of oxygen are required. So, moles of oxygen, we got no clue. All right. So, let's start with our given number. So, that's moles of water vapor. I'm not writing the state here just because this isn't part of the chemical reaction. You do need to write states in your chemical reaction, but not in the calculation part here, okay? All right, now we're in our molar ratio. So it's coefficient of what you want divided by coefficient of what you're given, okay? So we want oxygen. We're given water, or water vapor, I should say. Okay, so water cancels out. Now, what we're going to do is we're going to take 2.50 times it by 13 divided by 10. So what that's going to look like here is, let me turn that on, so clear that out. 2.50 times by 13 divided by 10 is going to give us 3.25. So 3.25, remember units, moles, and identity of the substance is going to be oxygen. All right, now sig digs. The given number in the question has 3 sig digs. Our answer has 3 sig digs, so we are done. All right, last example here. How many moles of precipitate should form if 3.89 moles of silver nitrate solution reacts with excess sodium sulfide solution? Okay, so some reminders here from our solution unit. The word precipitate, that just means that you got a solid product coming from the reaction of 2 aqueous solutions. That's what precipitate is. It just means you're looking for, or this is referring to, the solid product. Okay? Now, with solution, anytime you see solution, the state of that is going to be aqueous, and excess just means you've got an extra amount of this particular sodium sulfide solution, okay? How much you have in excess really doesn't matter to our calculation. It's more than you need in order to carry out this reaction here, okay? So, for example, like just to make it a little bit more relatable to you, right? If you were making grilled cheese sandwiches with slices of cheese and slices of bread here, okay, if you had 2 slices of cheese and an excess amount of bread, like 10 slices of bread, okay, you can only make 2 grilled cheese sandwiches because there's only 2 slices of cheese that you have to use up, okay? So the reason why we don't really care about an excess amount is it's just way too much to even like really limit our amount of product that we're going to get out of this reaction. And this kind of leads into the idea of a limiting reagent, which I'm not going to get into too much right now, but going back to the grilled cheese situation where we have 2 slices of cheese and an excess amount of 10 slices of bread, the limiting reagent in that scenario would be the 2 slices of cheese. Okay, limiting reagent just means what is the reactant that is going to cause the least amount of product to form. All right, going back to our question here. Okay, we have silver nitrate solution reacts with excess sodium sulfide solution. So that tells you your reactants for this question. And the key word that you're looking for to tell you that they are your reactants is the reacts with part. Okay, so silver nitrate. So silver is Ag, nitrate is NO3. Silver likes to have a +1 charge. Nitrate likes to have a -1 charge. That's equal to 0, so this is already balanced. Since it's a solution, it's aqueous. Reacts with can be translated to a plus sign, and it is reacting with sodium sulfide. In its solution, sodium likes to have a +1 charge. Sulfide likes to have a 2- charge. So we got to do crisscross applesauce. And that's going to be a 2 there. And now that's balanced. All right. So we got to predict our products. So what we're looking at is a compound is reacting with a compound. So this is going to be a double replacement reaction. Now, for double replacement reactions, I like just to focus on our positive ion switches with our other positive ion. But if you want to think of it more as your negative ion switches with your other negative ion, you can do that. Choose one way of thinking of it and stick with it. Don't think about both. Okay, so positive ion, for me, I like to focus on that. Switching with positive ions. So we are going to switch silver and sodium. And remember, the subscripts do not come along for the ride. The whole point of the subscripts is just to balance the compound. Okay? And the whole idea is just to switch sodium and silver. All right. So what that's going to do, if sodium comes and lives in the spot silver is occupying, that's going to give us sodium nitrate. Now sodium likes to have a +1 charge, nitrate likes to have a -1 charge. They balance out, so I'm done. I'll worry about the states later. Okay, now silver goes to live where sodium used to live, so it's going to bind to sulfide or sulfide ions. So we got silver, sulfide. Silver likes to have +1 charge. Sulfide likes to have -2. We got to do crisscross applesauce because 1 minus 2 does not equal 0. So there we go. All right. Now let's worry about what the states of these products will be. So what we're going to do to take care of that is we're going to go back to our data booklet. We're going to go to page 6 of our Chem 30 data booklet. We're going to first find our anion and then worry about our cation. So reminder, anion is the negative ion. Cation is the positive ion. So if I'm looking at sodium nitrate, remember nitrate like to have that -1 charge. So nitrate is the anion. So let's find nitrate. It's right here. Now, if I trace my finger down, it says most things are very soluble with nitrate, but let's just keep on going down and make sure sodium nitrate isn't in our list of exceptions. It's not. So what that means is that sodium nitrate falls under most, so it's very soluble. So it's aqueous. And we're going to do the same process here for silver sulfide. Oh, let's clean this up a little bit. So if we look along the top and we're looking for our sulfide ions, we're not going to find them. So what we do when we can't find a compound on our solubility table, if it's an ionic compound, you are going to assume that it is solid. Okay? So silver sulfide is an ionic compound. We're assuming it's solid. Okay, so back to talking about precipitate. Because this is our solid product, this is our precipitate. All right, before I move on, gotta remember that we have a skeleton equation right now. We need to balance it. So I'm gonna put little placeholders here. And you can ultimately start anywhere. So just arbitrarily, I'm gonna start with silver, because why not? So we got 1 silver going in, 2 coming out. So I need to make sure that's balanced. So 2 silvers going in, 2 silvers coming out. Okay, now that 2 didn't just affect silver, it also affected nitrate. So we have 2 nitrates coming in, but right now only 1 nitrate coming out, so I'm going to write a 2 right here. Now that 2 didn't just affect nitrate, it also affected sodium. So we got 2 sodiums coming out and 2 sodiums going in. So that's perfect. Now let's check sulfur. We got 1 sulfur going in, 1 sulfur coming out. That's balanced. Everything's balanced now. All right. So, how many moles of precipitate? Well, silver sulfide, that was our precipitate. We got no clue how many moles of that is going to form. So, if we have 3.89 moles of silver nitrate, so we know that, so 3.89 moles of this. All right, so now that we got our information organized, let's start this calculation. So 3.89 moles of silver nitrate. Now we got to do our molar ratio, because remember the steps went, step 1, balanced chemical equation. We finished that. Step 2, find your moles of your given substance. That was given to us in the question. Step 3, convert your moles of your known to your moles of your unknown using your molar ratio. So that's what we're doing right now. Okay, so what we want goes on top. We want silver sulfide. So we had a 1 coefficient there. Remember, if you don't write a number in front, there's a little invisible 1 right there. So 1 silver sulfide. Let me make that a little bit clearer. And then what we're given goes on the bottom, and we're given silver nitrate. All right, so how we're going to do this is we're going to take that 3.89 times it by 1 divided by 2. Okay, so we get 1.945. And that's moles. And since if you treat silver nitrate kind of like a unit, you have the same thing on the top and the bottom, so they cancel out. So we got 1.945 moles of silver sulfide. And remember, we also have to take into account sig digs. So looking at our question, we have 3 sig digs that we need our final answer to be in. So if I count 1, 2, 3, so there's my cutoff line. So I got 1.9, and this 5 behind the cutoff line is going to round the 4 up in front of the cutoff line. So 1.945 moles of silver sulfide.